Go ahead and start back up. We're ready for the final of Andy's 3 principal lectures, the final talk of the conference. But remember, we do have a problem session a little bit later on, so don't forget about that. But let me turn over to Danny for his final talk.
Okay, so thanks again, and thanks for everyone for, I guess, lasting till the end of this conference. And I think since this is the last talk, I really think we should start by giving the organizers a big hand. So, very fun and valuable conference, at least to me so far. So this is a picture of a zipper. So this is a pair of subsets of a two-sphere. The two-sphere, well, I mean, you can only see one side of it, I guess, but this is the sphere at infinity of hyperbolic through space. And there's implicitly a group. The group in this case is the fundamental group of, actually it's an orbifold, not a manifold, but you could take a subfinite index subgroup, which was a manifold group. It's a certain orbifold filling on the figure 8 knot complement, and it's a filling for which the resulting orbifold fibers over the circle. And just as for manifolds, closed hyperbolic 3 manifolds fibering over the circle, to closed hyperbolic 3 orbifolds fibering over the circle, the only issue being that there's torsion in the group. You get a pair, you get a group acting on the sphere at infinity, and you get a pair of disjoint, not empty, part connected, group invariant subsets, Z plus and Z minus. Z plus in blue, Z minus in red, or maybe the other way around, Inu's notation. And you can see, I mean, if I kind of zoom in on it, maybe it's, I don't know if you can see this, but oh, that's not the right thing to do. Okay. You know, you zoom in on it, it's just really trees, pair of trees. So understanding these things is really just understanding trees embedded in S2. Right? You pick a finite, or pick a point in the zipper, the G orbit of it is a countable set for any finite subset. The convex hull of that in the zipper is just a finite tree, just an ordinary finite simplicial tree. It's embedded in S2 in a perfectly straightforward way. In fact, geometrically, I believe in this particular case, the arcs are, well, they're not quite rectifiable, but they're uniform quasi-arcs, so they're really quite mild, topologically speaking. And you can really just draw pictures of it. Once you can find one arc in one of the zippers, well, you just translate it around. The action is sort of minimal. The image is going to be kind of dense, and the union, you just take bigger and bigger subsets of your group, and you translate the arc around, and you draw it, and you get a red tree, and then you do the same with the blue arc, and you get a blue tree. And so, point being, it's a very concrete and tangible object, which somehow just manage to exist in great proliferation for many, not all, but many closed hyperbolic 3 manifolds. And associated just to this structure, just the existence of these zippers, you get a universal circle and a pair of invariant laminations, so an action of your fundamental group on a circle preserving a pair of laminations. And hopefully this gives you a way to recover some interesting dynamical information that was associated to whatever it was that gave rise to the zipper in the first place. Okay. So I'm going to move to Blackboard now. And what I want to sort of emphasize here is that it's a good thing that the axioms defining a zipper are such a small list that we don't a priori require a lot of facts about them, that we can just sort of deduce them axiomatically from the setup. The most important is the group the group invariants, the disjointness, and the path connectedness. And so, conceptually, the idea is, well, if we have any old path connected space, and two maps, E plus, E minus, to S to infinity, for which the images are disjoint, well, you get some disjoint path-connected subsets, and if you have a group acting here, and a group acting here, and the actions are over here at least is minimal, then you get a zipper. And so it doesn't really matter what this space is, it can be extremely general. You get, at the end of the day, a rather interesting piece of dynamical structure as output. In fact, this space here, well, path connected, really it's only the image that needs to be path connected. So at the end of the day, we could look at something which is a kind of combinatorial approximation of a path connected set over here, maybe just a countable collection of objects, or maybe, well, we'll sort of, I'll talk about something very concrete at the end of the day, something which is not obviously path connected, but for which the image is path connected. But I want to sort of leave this up here as a kind of high-level template for the kind of thing that we're going to try to achieve. So I want to indicate exactly how one obtains objects of this kind. And so, well, we already saw an example. The example was we have M closed hyperbolic and X a quasi-geodesic flow without perfect fits. And then P here was the leaf space of the one-dimensional foliation on the universal cover. E plus or minus were the endpoint maps. Without perfect fits, here if you want a definition, in this context it's just equivalent to the statement that these have disjoint image. And so another example for the example is, so this is implied for instance by e.g. M fibers over the circle and X is transverse to the foliation by surfaces. So I want to take another look at this particular example from a sort of course point of view. So there's a perspective on what it means for a hyperbolic, for a three-manifold to fiber over the circle, which is topological, well, it's filled up by these surfaces. But there's a group theoretic perspective on what it means for a three-manifold to fiber over the circle. And this is an observation, really a rather profound observation due to John Stallings. So we have here just, let's say, closed, maybe I have to say irreducible, three-manifold. And supposing I have a homomorphism from pi1 of M to Z, so let's let this be a surjective homomorphism. I can look at the kernel, and so this is a normal subgroup of pi1 of M, and well, this normal subgroup, it might be finitely generated, and it might not be finitely generated. Okay? And Stallings, very famously, says that K is finitely generated if and only if, well, I'll say phi is induced by a fibering of your three-manifold over the circle, in which case the kernel is pi1 of the subgroup, which is certainly finitely generated. Not only is it finitely generated, it's finitely presented. Well, that's true for three-manifold groups. If they're finitely generated, they're finitely presented. But a priori, the key thing is that the finite generation is equivalent to the fibering. And so this is sort of a geometric picture. So in geometric group theory, If we take G a finitely generated group, we can think of it as a metric space by, for instance, taking the Calegari graph and making, with respect to some finite generating set, and giving every edge length 1. Or we could think of the group acting co-compactly by isometries on some nice space, and up to quasi-isometry we could replace the group with the space that it acts on. But in any case, you can think of the group somehow as a, well, nice separated net sitting in some nice metric space. Here G somehow is the group, but with its metric, with its quasi-isometry class of metric. And then if you have a homomorphism from G to Z, a surjective homomorphism, it's not surjective, it's not that interesting, surjective map to Z, so think of that as sort of, well, it's a coarse map here to Z, and again, Z, you can think of it as coarsely not so different from R. What you can do is look at, well, you can look at the level sets, but we don't want to look at exactly the level sets, we want to look at the coarse level sets. So you have to quantify things appropriately. But what does that mean? Roughly speaking, you take bounded things in the image of a certain size, big enough in terms of the constants that are going on, look at their pre-image over here. So that's a bad letter. B for bounded, I guess, I don't know. B inverse B. And then what you want to do is, say, relate the algebraic properties of phi to, well, not exactly the topological properties of phi inverse of B, because it's not well defined if the space is only given to you after fuzzy isometry, but the coarse topological properties, the coarse connectivity properties. And so the idea here is that the kernel of phi is finitely generated corresponds to the condition that these sort of coarse level sets of phi are coarsely connected. So this is, I guess, at the end of the day, first stated and proved by Gromov in sort of 93 asymptotic invariants, blah, blah. For precise definitions or proof, take a look there. But it's not so hard to figure out if you want to sort of think of it yourself. Okay, so this is for group homomorphisms. And so the idea then is, well, these coarse level sets are coarsely connected. And so what is sort of the set P in this context? The set P in this context, again, we want to describe it in the coarse world. We want to let P, really need another board. Well, all right. So here P is going to be a set of quasigeodesics in G. And quasigeodesics here doesn't even need to be something topological, doesn't even need to be R, it could be just a sort of a discrete set. I'll just say parameterized quasigeodesics in G such that phi restricted to this quasigeodesic is approximately a homomorphism. If you like, it's a bi-Lipschitz map onto the image, coarsely speaking, up to an additive constant. Okay? So the idea is we can look at sort of these infinite ascendings. Hard to draw a discrete bunch of dots, so I'm going to kind of draw them kind of with arrows joining them, but some discrete set like this, where the size of the intermediate hops are all bounded, and the values under phi, well, maybe they're going up a little bit and down a little bit, but they're kind of making steady progress in the upward direction. And so, by the way, the very fact, if we have a homomorphism phi, a homomorphism, of course, is a Lipschitz map, and so the very fact that this value of this Lipschitz function is making definite progress implies that this thing is a quasigeodesic. And so if G was a hyperbolic group, so let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G is hyperbolic, then, well, this is a hyperbolic group. So let's say, e.g., G just in the sense of geometric group theory, this geodesic here, which I guess I'm going to call quasi-geodesic script P, heads off to infinity in positive direction. E plus of this script P is some point in the boundary, the Gromov boundary of the group. E minus, if you go in negative time, E minus of script P is in the boundary at infinity of the group. And these things are disjoint, because if you had two uniform quasi-geodesics that headed off to the same point at infinity, and the value of phi was going to plus infinity on one and negative infinity on the other, the distance between these geodesics or quasi-geodesics would need to be getting bigger and bigger, because it's a Lipschitz function. But the quasi-geodesics that ending up at the same point at infinity, there has to be a bound on their distance. Okay, so that's in contradiction. And it implies that E plus and E minus, the images of them on these sets, are disjoint. So E plus P, well, it's E plus, E minus P, Z minus are disjoint. And we, here, I didn't say what kind of quasi-geodesics, maybe we have to insist on some constant. And whatever we do here, we're going to take a subset such that it's invariant under the action of G. So it's a G invariant subset. So G is going to act on this set of quasi-geodesics just by left translation. Okay, so some class of quasi-geodesics, uniform quasi-geodesics, invariant under the action of G. I mean, this property that phi is a approximate homomorphism, if we quantize things appropriately, that's definitely invariant under the action of G. And so we get a pair of G invariant disjoint subsets Z plus and Z minus of the Gromov boundary of the group G. What about path connectivity? And what does that have to do with coarse connectivity of the level sets? Okay, so the idea is, well, if we want it to be the case that the images are path connected, we need to be able to interpolate between any two endpoints of any two of these guys by a sort of one parameter family. So supposing we have one of these guys going up, we have another one of them going up, and I don't know what it's doing exactly. Here's another one, whatever it is. So here's I don't know, Q or something. And so P and Q are going to hit two particular points at infinity. We'd like to interpolate between them. So can we interpolate? And what you see in this context is that the condition that the coarse level sets are coarsely connected is actually enough to be able to let you interpolate between any two P and Q. And so maybe I'm going to write that over here as a lemma. So if the coarse level sets of phi are coarsely connected, and in different contexts people use different words for this, but in the context I grew up in, this is referred to as uniform. So one would say here that phi is uniform. So uniform homomorphism from a hyperbolic group to Z. If the coarse level sets are coarsely connected, then I'll just say E plus and minus of this subset set of quasi-geodesics P are path connected. And let me give you the idea of the proof. The idea of the proof is, well, okay, so let's suppose, for the sake of argument, there's a point on the one of them P, and there's a point on one of them Q, and maybe they're distance one apart. Whatever they are, they kind of meet the coarse level set of 0 at some point. Maybe they start distance one apart, and then they head off in some direction. So at the next level, the level of 1, maybe this guy goes up to here, this guy goes up to here. So the coarse level sets are coarsely connected. So even though these 2 points might be quite far away in the level set at distance 1, they're still connected in the level set at distance 1, so you can join them by a path in the level set at distance 1, well, where the hops aren't too big and where you don't need too many hops. Okay? And then you go up the next level. So the next level, this guy goes up here, and this guy goes up here, and then, well, this is at the level 2, these things in the middle, I want to interpolate, so what do? I say, well, there's something I can do. I can go in the positive direction, because, for instance, the group acts, so whatever this edge is, I could take the starting point to here, or I could take the starting point of this one to here, or any other one, so I can put something here. So there's something in the middle I can do, which is a guy which is not too big, and each of these, which goes up to the next level, and again, I can sort of interpolate and subdivide, and then just keep going up. Etc. And what am I doing here? I'm constructing a family of quasi-geodesics. What are the quasi-geodesics? The quasi-geodesics are, go up a unit, and then you can go wherever you like on one of these segments, but don't go sort of more than a bounded distance away. So I can go all the way anywhere along here. Then go up one, and I go either to the left or to the right, but I can't go too far. I can't go, say, past this one here. And then I go up, and then and so on and so forth. So you think about it, these different choices you can make at each stage are like, you know, the numbers in a decimal expansion of the numbers between 0 and 1. And topologically, that's the correct topology on this set. At the end of the day, you get a continuous map from the interval from 0 to 1 to the set of endpoints. And it gives you an interpolation, a path, in the image of P, E plus of P, between E plus of one of the points and E plus of the other. So that's sort of more or less the proof of the lemma. Okay, that's great. So this is yet another proof that you get a zipper if you have a three-manifold group, a hyperbolic three-manifold group, and you have a homomorphism to Z, surjective homomorphism to Z, whose coarse level sets are coarsely connected, equivalently, whose kernel is finitely generated, equivalently by Stallings, which fibers over the circle. But I'm not using the fibering over the circle. I'm not using any topology at all. All I'm using is that G is a hyperbolic group, and that the coarse level sets are coarsely connected. So if it comes to that, I don't even need phi to be a homomorphism for this to work. All I need it to be is something which is coarsely a homomorphism. Well, there is a sort of a theory of such things. Such things are called quasimorphisms. Let me tell you about quasimorphisms. So let's let G be a group, and a quasimorphism is going to be a function from G to, it could be to R, it could be to Z, probably going to pick one of those two things. Let it be to Z for the sake of argument. Okay, I'm going to let it be to R for the sake of argument. It's a function from G to R, just a function, not necessarily a homomorphism. If it were a homomorphism, then phi of G times H would be equal to phi of G plus phi of H. For a quasimorphism, this is not equal to the sum of these two, but the difference is bounded by something called the defect, just some constant. It's just some constant, crucially, which is independent of the elements G and H that I have on the left-hand side. So phi of G times H is equal to phi of G plus phi of H plus or minus a constant of bounded size. Okay? So that's what quasimorphisms are. People who have heard me talk about quasimorphisms probably know that I usually want to impose one further condition, which is that you want your quasimorphism to be a homomorphism when restricted to each cyclic group. I'm not going to impose that here. You could if you wanted. That's called a homogeneous quasimorphism. But I'm not going to insist my quasimorphisms are homogeneous, but let me give you some examples. Example 1, any bounded function on any group is a quasimorphism, obviously. Put that bound on the right-hand side 3 times. 2, any homomorphism from G to Z or up is a quasimorphism where the defect is just 0. One more example. Let's let G be pi1 of M, where M is now a closed, negatively curved manifold. Doesn't have to be hyperbolic. Maybe just the curvature is bounded below and above by 2 strictly negative numbers. And we pick a base point, so it's really pi1 of M based at some point. And let's let alpha be any one form on M. Just any Durand one form, real Durand one form. What I can do is, for each element G in pi1 of M based at X, there is a unique geodesic gamma sub G, is a geodesic loop, based at the point X, representing the base homotopy class associated to the element little g. So here's my manifold, here's my point, and I get the geodesic, there it is, gamma sub G, and I define a function, phi, maybe phi sub alpha, of G is just equal to the integral of alpha over this geodesic. So I just integrate alpha. Okay? Well, if I have 3 elements, G, H is the loop gamma H, and then I don't know what the loop. Yeah, anyway, gamma GH, or something like that. If you lift to the universal cover, the picture becomes a little bit nicer because these 3 loops lift to the 3 edges of a geodesic triangle. And since the curvature is negative and uniformly bounded, this bounds a disk, and the area of this disk is less than or equal to, I don't know, pi times, maybe it's the square root of the curvature or something. Something like that. I don't remember if it's 1 over or whatever it is. Some constant depending on the curvature bound. In particular, the value of alpha on this guy, followed by the integral of alpha over this guy, is equal to the integral of alpha over this guy, except it's not. The difference is the integral of d alpha over this triangle. So phi alpha g plus phi alpha h minus phi alpha gh is the integral over this triangle d alpha, which is bounded by the area of the triangle times the norm of d alpha, whatever that is. And M is a compact manifold, so these are just finite numbers. Okay? So this is an example of a quasimorphism, very simple example. Here's another example of a quasimorphism. If we have a group, the group of homeomorphisms, orientation-preserving homeomorphisms of the circle, well, it acts on the circle. There's a central extension of this group, which is sometimes usually denoted by putting a little twiddle over it. So it's a central extension of the group of orientation-preserving homeomorphisms of the circle. This is the group of homeomorphisms of R, the universal cover of the circle, that commute with integer translation. So Z here, the kernel, are just the things that map to the identity here, so they just lift to the group of integer translations. And that's the center, so things that commute with those are the things here. Well, there's a function from this group to R, sometimes called ROT, Poincaré's rotation number. And the way it's defined here is if I have an element, well, it acts on the circle by homeomorphisms, but we've chosen a real valued lift of it. So it's acting on the line by homeomorphism. And what I can do is I can take a big power of alpha, see what it does to say 0, and divide by n. Doesn't really matter if I subtract off 0 or not. And you can check Poincaré proved theorem, Poincaré. This guy here is a quasimorphism on what? On this group here. The defect is like 2, or maybe 1, something like that. Okay, so you get, I want to say, quasimorphisms arise in nature in 2 different ways. 1 from hyperbolic geometry or negative curvature, 2 from causal geometry or sometimes symplectic geometry of topology. Okay, so these are the 2 worlds in which quasimorphisms tend to arise in nature. So now, let's suppose we have a finally generated group, and we have a map phi from G to Z, which is surjective, which is now no longer assumed to be a homomorphism, but just a quasimorphism. By the way, if you have a quasimorphism whose values are real, you can just take the 4 of the values, and that will be a quasimorphism whose values are integers. The defect will go up a little bit, but not too much. So it doesn't really hurt anything to make the quasimorphism take values in Z. And then we say that phi is uniform if the coarse level sets are coarsely connected. And the picture looks exactly like this. And we define P to be some set of parameterized quasigeodesics in G, such that the value of phi restricted to these quasimorphisms is approximately a homomorphism. You need to quantify things as before. And we want this set to be G invariant. It's a little exercise, you can do this. And exactly as before, the images under the positive and negative endpoint maps are disjoint and group invariant for exactly the same reason, which is that a quasimorphism on a group, like a homomorphism, is also a Lipschitz function. And so if the values are growing linearly on subsequence, it's a quasigeodesic, and it's growing positively on one and negatively on the other, they have to go to different points at infinity. Exactly the same argument. Exactly the same argument, I wish, maybe I've erased it, I think I did erase it, but exactly the same argument is going to show if the coarse level sets are coarsely connected, that the endpoints, E plus and E minus, not just disjoint and G invariant, but they're path connected. Okay, I showed you how to construct a path. The same proof works. I never used that homomorphism problem. So the conclusion is, if you have a hyperbolic group G, and you have a uniform quasimorphism, so this is the definition, I guess, of a uniform quasimorphism, you get a zipper, meaning you get a pair of disjoint path-connected subsets of G invariant subsets of the Gromov boundary. In the special case that the Gromov boundary is a two-sphere, you get more, namely exactly the arguments that Inu spelled out this morning imply your group G acts on a circle, a universal circle, leaving in invariant a pair of laminations, lambda plus or minus. Do you know any examples of hyperbolic groups for which the Gromov boundaries are two-sphere? Well, yes, we do know such examples, namely fundamental groups of hyperbolic 3 manifolds. Do we know any other examples? Essentially not. Canon conjecture says if the boundary is topologically a two-sphere, up to finite index, you should be the fundamental group of a closed hyperbolic 3 manifold. But that's a conjecture. Maybe true, maybe isn't. What's true is if you have a group whose boundary, hyperbolic group, whose boundaries are two-sphere, and you have a uniform quasimorphism on it, then you get zippers. You get an action on a universal circle, blah, blah. All right. Another example, just to indicate that this is not completely vacuous, you might ask, are there any examples of uniform quasimorphisms on hyperbolic 3 manifolds? The answer is yes, and actually, I believe there's a lot of them. In particular, example, so there exist examples of homology 3 spheres, M, which are closed hyperbolic, such that pi 1 M admits a uniform quasimorphism, and therefore there is a zipper, associated zipper Z plus or minus for pi 1 M and a universal circle. The reason I say homology 3 spheres, well, if you have a 3 manifold that fibers over the circle, well, the fibering over the circle, the map to the circle, induces a surjection from pi 1 onto Z. In particular, you're not a homology 3 sphere. You have a homomorphism from pi 1 to Z. So it's interesting that there are examples of hyperbolic 3 manifolds, closed hyperbolic 3 manifolds, which are homology spheres, for which there are such uniform quasimorphisms. And I'll give you a very explicit, I'll tell you a very explicit way to construct some. The actual construction is a little bit involved, but I'll say roughly what's involved. So example of example. So this is a definition due to Thurston. You say a manifold, 3 manifold M, slithers over the circle if the universal cover fibers over the circle in such a way that pi 1 of M, so it fibers over S1, so somehow it's a bundle over S1, and pi 1M acts on the universal cover, acts by bundle automorphisms. Okay, so this is a little bit weird. You think about it, this non-compact 3 manifold fibering over the circle, how can it do that? Well, the fibers can't be connected. So what are the fibers here? The fibers are just a Z worth of planes. And if you think of the universal cover, therefore, the universal cover has a foliation by planes, which are the connected components of the fibers of the fibration over the circle. So, in particular, I mean, the universal cover fibers over the universal cover of the circle, which is R, which is a foliation by planes, and pi 1 acts by bundle automorphisms, which means the induced action of pi 1 on R is contained inside this group, homeo plus S1 twiddle. Yep. And therefore, there's a quasimorphism, rotation quasimorphism, to R, which is approximately equal, in fact, just to this function R. It's bound a distance away from it. So the coarse level sets of this quasimorphism are also the coarse level sets of this fibration. In particular, they're coarsely connected. They would be connected in this particular bit here. So this is a uniform quasimorphism. So examples would be, let's say, example. So here, this foliation, maybe I should call it F twiddle. F twiddle descends, therefore, to a taut foliation on the 3-manifold M. And an example of such a slithering would be that this is the stable foliation of the geodesic flow on the unit tangent bundle of sigma, where sigma is a hyperbolic surface. And if you want to think about that, that's 3-manifold is the total space of a circle bundle over a surface. And the Euler class of the bundle is the Euler characteristic of the surface, which is negative. In particular, this is a rational homology 3-sphere. You could find examples which are integer homology 3-spheres, but anyway, this is a rational homology 3-sphere. And then certain branched covers of this, you can take branched covers of this. So we take another manifold, let's say N, it's a branched cover, maybe over some knots in this guy here, and you want them to have the property that the pre-images of the knots is a collection of sort of loops here that do something not too terrible, that they kind of are part of the global product structure of the universal cover. So that when you take a branched cover of this thing here in a hyperbolic 3-manifold, the end result in the universal cover is a foliation which comes with a branched cover leafwise over these things here. But because these are sort of part of, there's a global topological trivialization here, which is certainly not pi1 invariant, but tells you that the leafwise branch cover here gives you a foliation of R3, product foliation of planes R2 times R. Okay? And it still comes with this structure map to R. The action on R is still this map by bundle automorphisms, and you get your uniform quasimorphism by this rotation quasimorphism. And you can arrange for this branch cover to be a rational homology sphere or a homology sphere. So lots of examples. I think I'm going to end a little bit early because it's sort of the end of the conference and this is a lot of math to digest. But maybe just make one more comment, which is that one of the motivations for sort of studying this is there's a conjecture in 3-manifold topology that says that 3 different certain kinds of structures on irreducible 3-manifold should be equivalent. The 3 structures are that there is a co-orientable taut foliation, 1. 2, that the fundamental group is left orderable. 3, that there's some non-trivial Higard-Fleur homology. It has been conjectured that these 3 categories, classes of 3-manifolds, irreducible 3-manifolds, are identical. I personally continue to think this is a ridiculous conjecture, almost certainly false, despite Nathan Dunfield having produced absolutely whopping amounts of computational evidence that it is true, at least amongst very small volume manifolds. Most manifolds do not have small volumes, so I don't believe any of that evidence. But you can then ask, well, each piece of this conjecture is very difficult. It turns out if you have a taut foliation, then the Higard-Fleur homology is non-trivial. That direction is true. It turns out if you have a taut foliation, well, the fundamental group is not necessarily left orderable, but it is at least circularly orderable. Why? Because there's a universal circle. Taut foliation gives rise to a universal circle. And so, if you believe this conjecture, which I don't, one way to try to prove it might be to say, let's start with a left order and see whether we can cook up out of that a certain kind of action on a circle, a universal circle, which preserves a pair of laminations. Because that's what you would get if you had a taut foliation. Okay? And so, certain kinds of left orders, what we call uniform left orders, similar kind of argument to this, it's a little bit more delicate, implies, again, that there are zippers and therefore universal circles. By the way, here's where left orders could come from. You might have a homomorphism from your fundamental group to the group of homeomorphisms of the circle, and you might be a homology sphere, in which case that homomorphism would lift to this central extension, and then you would get an action on R, and you would be left orderable. So a lot of the reason that three-manifold groups are left orderable is that they have some non-trivial homomorphisms to the group of homeomorphisms of the circle. Some of them arise, very interestingly, from number theory / hyperbolic geometry. If you have a hyperbolic three-manifold, the fundamental group is conjugate into the group PSL2K for K some number field. Well, it might be the case that that number field is Galois conjugate into a real field, in which case you would have a faithful, certainly not discrete, but faithful representation of your fundamental group into PSL2R, which acts on the circle by homeomorphisms. If your manifold was a homology sphere, or a rational homology sphere, and the Euler class happened to be 0, that action would lift to an action on the line, and you would be left orderable. This is, in fact, one of the key ways in which people show that certain three-manifold groups are left orderable. That action on R, because it came from an action on the circle, is associated to a quasimorphism. Conjecture: the quasimorphisms that arise this way are uniform, and therefore give rise to zippers, and therefore give rise to universal circles. And so this is evidence towards a conjecture that I don't believe, that left orders should give rise to taut foliations. What I do think is true is that some mysterious structure is common in all three circumstances, and the evidence for this conjecture we should really think of as evidence towards the existence of this common substructure, and that's what we should be looking for. And so zippers are a sort of a step in that direction, and I want to stop with that.
I have a question I'd like to start up. So the beauty of your theory of zippers, the example you've shown depends on the boundary of that group being a two-sphere.
Mm-hmm.
Are there other hyperbolic group boundaries where you get an especially nice?
You know, so we now know, contrary to certainly my wildest dreams, that there are examples of hyperbolic five-manifolds that fiber over the circle. And so they have zippers. What the hell are they?
Other questions? Yeah, go ahead.
So how critical is the condition for G being hyperbolic? Can it be some other kind of distribution like cat 0?
That's a very good question. I haven't thought about it, so I don't know the answer, but it certainly makes a lot of sense to talk about quasimorphisms which are uniform or not in groups in many contexts, showing that the endpoints are disjoint. For hyperbolic groups is easy because quasigeodesics with the same point are asymptotic, but if you another way of doing it, that's a way of doing it. There are sort of generalizations of the idea of zippers where you allow the zippers to touch but not cross. Let's not go into that, but maybe, certain cat 0 spaces, there might be parabolic subsets of the boundary where things can kind of touch but not cross, and there's sort of an analog there. I don't know. I think that's an extremely good question. I think the whole theory is very easy to play around with just because it's just, at the end of the day, comes down to a very small list of axioms, and they're very robust constructions of them, depending really on extremely fundamental topological conditions like coarse connectivity. So I think there's a lot of ways in which one could do something with it. I know nothing whatsoever about what would happen if you did that. I think it would be a great idea to
Other questions? Yeah.
So could you repeat what happened when you get a branch cover of the...
Oh, yes. So I have the unitangent bundle of a hyperbolic surface. Definitely slithers over the circle, and the stable foliation or the unstable foliation, the geodesic flow is example of the foliation there. But that's not hyperbolic. So you want to take a branch cover of it, which is hyperbolic. Well, if you take a branch cover of a three-manifold with a foliation, and the branch locus is transverse to the leaf of the foliation, then you get a taut foliation on the branch cover. However, we want the leaf space to be R because it's giving us the structure map, the slithering, and it gives us the homomorphism. So we don't want to take an arbitrary branch cover, because if we did, some of the branch locus might go out to infinity and not sort of go all the way up. So you have to be a little bit careful about how you choose the curves that you branch over in order to show that, well, the pre-image of this sort of knot in this 3-manifold is an infinite grade in this 3-manifold, and you want to show that it's topologically trivial grade, not equivariant, but topologically trivial. So there are some tools to do this. Cass and Jung-Rice had a sort of particular way of doing it for certain kinds of grades as part of their proof of the cipher conjecture, blah, blah. There's other contexts in which it's true. In this context, in many cases, you can just directly show that the universal cover has this nice product structure, and therefore the 3-manifold slithers over the circle. Sorry, the hyperbolic 3-manifold is the branch covers fibers over the circle. But there's some technical conditions to check. Yes. Yeah.
Maybe a bit of a vague question, but when you got to this concept of separates in the first place, was it through working? You listed like 4 examples. You've gone through them in this talk. So was it kind of going through examples and seeing it naturally come up? Or
You know,
it seems very natural from the start.
No, very, very unnatural. So we've been playing around with them long enough now that it seems a little bit natural. And if anyone sort of knows my career, then you probably know that I've really only done like 1 or 2 things in the same, somehow people do the same things every decade. But, you know, quasimorphisms, foliations, circles, whatever, it's all this sort of bag of whatever. And of course, everyone knows, not everyone, but everyone knows the Cannon-Thurston picture of these sphere-filling curves. You know, I always sort of had a view of these sphere-filling curves as being like obtained by like embedded curves that are wigglier and wigglier and degenerating the limit. And I wanted to have an implicit way of thinking about the complementary regions, but until Inu and I came to this joint project, it never occurred to me that one could find, how could you have these 2 disjoint path-connected G-invariant sets? It doesn't make sense, but there they are. Yeah. They're not closed.
All right, let me remind everybody, we have a problem session. Let's give ourselves about a 10-minute break, but let's also give Danny a round of applause for 3 terrific